And welcome to 17.4, where we're going to discuss calculating heats of reaction. In this particular section, we are going to take a look at how we measure the amount of heat that is absorbed or released by reactions. And we're going to be discussing in particular Hess's law, which is very, very useful. The reason why this is so useful is because sometimes reactions are so slow that it becomes very difficult to measure the actual heat change in that reaction. In addition, you might have a reaction that produces an intermediate or is an intermediate step in a series of reactions, and it's very difficult to isolate it. Or you simply might not want to destroy the reactants that you're working with, and you want to be able to still understand how much heat is going to be exchanged when a particular reaction takes place. So, here's the deal. Hess's law gives us a tool to manipulate equations to determine the energy changes indirectly. All you have to do, or all Hess's law states, is that if a series of reactions, or if you add up a series of reactions, if a series of, we'll say that they're thermochemical equations, if a series of thermochemical equations are added to give a final equation, then the heat of reaction for that final equation is the sum of the heats of reaction. That says reactions right there, by the way. For the series added. Now that sounds like a mouthful, but it really is quite simple. If you add up a bunch of reactions, the final equation, the delta H for that final equation, is just adding up all the delta H's of all the equations that you added up. Now this comes in really handy when you want to figure out the heat of reaction for when a diamond turns into graphite. This is a spontaneous process that takes place over millions of years. And so there's no way to actually observe this reaction taking place and to take an accurate measurement. So what you can do is simply this. Take a diamond and burn it in oxygen and to produce carbon dioxide. Take graphite, burn it in oxygen to produce carbon dioxide, and compare the results. When you do these two reactions, when you burn a diamond, the delta H for the reaction is going to be a negative 395.4 kilojoules per mole. The delta H of reaction, you could call that delta H of combustion as well, for the burning of graphite is going to be a negative 393.5 kilojoules per mole. So if you look at this on an energy diagram, say this one is your carbon, well, this will be the diamond, plus your oxygen. When this goes to carbon dioxide, if that's your reactant, let's say this bottom line is your product, your CO2 gas. As you go from reactant to product, this is going to release a negative 395.4 kilojoules. When you do the same thing with graphite, so we'll say carbon solid graphite plus your oxygen, when you do that, This one releases a negative 300, or the change is negative 393.5 kilojoules. The difference between these two, notice they're going to the same product. They have all the same reactants except for one's a graphite, one's a diamond. So therefore, the only difference between these two is the difference between the graphite and the diamond. Another way that you could think of this is by simply adding up the equations. So instead of having this reaction going in this direction, which would release 393.5, you could switch the direction and say we're going to go from carbon dioxide and break it down into carbon, the graphite, and oxygen. That would have to add 393.5 kilojoules. And so therefore, if we write the equations out, the diamond going in the forward reaction but the graphite going in the reverse reaction, we can write out their delta H's. This is a negative 395.4 kilojoules. This one going in this direction, the reverse of the original, will be a positive 393.5 kilojoules. And now notice what happens. The oxygens, if you add these up, the oxygens divide out, one on the reactant side, one on the product side. The CO2 on the reactant side cancels out the CO2 on the product side, so all you're left with is the carbon in the diamond form turning into carbon in the graphite form. And the delta H for this reaction will simply be the sum of those two, which is going to be 1.9 kilojoules of energy. So we can calculate the energy change as diamond goes to graphite over the course of millions of years without actually observing it. If you take a look at the diagram, that difference will be 1.9 kilojoules right there. Alright, that is basically what Hess's law boils down to, is the ability to add up equations and to determine the energy change by the sum of its steps. Alright, so let's go ahead and try this one out. Using the following equations, determine the heat of reaction for the given reaction. So here's the how you would handle this, and it's kind of like a game. You want to have calcium on the reactant side. So this reaction here, you want to write out just as it is written. So we're going to write that out just like that. And the delta H is going to be a negative 62.8 kilojoules. Now remember, that is per mole. We usually just write it as kilojoules because it's assumed to be per mole. Okay, so that's this one right here. Now let's take let's go to this bottom one first. I'm not quite sure what we want to do with the middle one yet, but let's take a look at this bottom one, because I want to get the calcium carbonate, which is right here. I want to get that on the product side. So I'm going to reverse this reaction, which also means you have to reverse the sign on the delta H. So we're going to write this out as CaC2 solid plus 5/2 oxygen. Now remember, those are moles, so you can have 5/2 moles, and that would produce calcium carbonate and carbon dioxide. And the delta H for that then is going to be the reverse of this, so it's going to be a negative 1538 kilojoules per mole. Now when we do that, notice that the calcium carbide is going to divide out, the CaC2. This actually should be CaC2. This L should not be there. It should be just CaC2. And now we're left with calcium plus carbon plus oxygen produces the calcium carbonate and the carbon dioxide. Well, over here we're good with the calcium and the carbon, but we want to get rid of the carbon dioxide over here, plus we have a little too much oxygen up here. So we have one more equation that we want to deal with, and that is this middle one right here. And if we write that out as it is written, CO2 gas, not a plus sign there, we're going to go with produces carbon, which will be a solid, plus oxygen gas, and the delta H for that reaction is still going to be 393.5 kilojoules per mole. Alright, let's see where that gets us. Well, if we take a look at what we can cancel out, the carbon dioxides will cancel out, one on the reactant side, one on the product side. Notice we have one carbon here, we have two here, so this is going to change into a 1. And over here, we have oxygen and we have 5 half oxygen. Well, if this is just a 1, we can write this as 2 over 2. So 2 over 2 will cancel off with this, and this will make it 3 over 2. So that if we add this up, we're left with calcium plus carbon plus 3 halves oxygen producing calcium carbonate. Everything else has been canceled out. And then the delta H for this reaction will simply be the sum of all those steps. So you have a negative 62.8 plus a negative 1538 plus 393.5, and it looks like we have a negative 1207.3 kilojoules per mole. I'll just write it as kilojoules because it's assumed to be per mole of reaction. That is basically Hess's law. You can add up a series of reactions and the delta H's will be added up as well. If you reverse a sign, you're going to have to, if you reverse a reaction, you're going to have to reverse the sign. Okay? We'll explore a little bit more of this in the next podcast. See you next time.